Alright, let's go over the code in the paper. So we start here. So in addition to the code, there is a landing page where you can use a web application to engage the basic commands of the VCF querier. We also have the documentation on the code here, the actual code, it's here, and so on. And when I'm done recording this video, there is also going to be a tab here for YouTube. Notice also the notebook and issues. A particular feature of the way this is being disseminated is the existence of a public chat box where people can ask questions, share experiences, ask for help, etc. Alright, so back to the code now. So let's jump to the method section. There it is. We have three key methods that are supported. One is the connection of a local object with the remote VCF file. And the claims in all three of them is going to be that the execution times are surprisingly low, and we can indeed use distributed collections of VCF, large VCF files, as if it was a shared data space. So let's make sure this is clear now. So I'm going to start by linking a remote file. We're going to do this one. So clean var. Can even copy them directly here. Sorry, not clean var. So that is snip, and there they are, 16 gigabytes, 15 gigabytes. So I'm going to copy the link address, and I'm going to do what I promise here, that I can create an instance of the VCF object that is a connection to the remote VCF file. Okay, so what I'm going to do next is open the DevTools. For those who may not be familiar, I'm going to close them again, and I'm going to do it manually. Moving this a little bit here. So you see here on top, more tools, developer tools here, and you have the same view. Okay, back here, and of course there's a shortcut to open and close quickly. So I'm going to clear here. Let's make the connection then. So let's call it V. We could call it V. Await VCF, and now the URL. So here we go. It's a little bigger. 1, 2, 3. There it is. So in really a very short amount of time, there it is. This is on the second. You get a connection to the remote object, where you get not just the size. Where is size? There it is. Size 16 billion bits, and the metadata. So here, notice that all of this has to be not just retrieved, but as the decompression key has to be found, and the compression has to take place. So that's how fast it is. If you get lost on what exactly these commands are doing, this figure 1 may be useful. So you have a fixed collection of chunks that is compressed in the creation of the VCF file, and then it's placed in a remote location. From one or more client-side environments, one can use this remote location essentially as if it was a local database. So the challenge there is that when we make a query, the query comes here, the next key has to be found, and then from here on, the compressed chunks are taken out and decompressed. So that's how the tool works. So the first step is to connect, and we have it now under V. So this V object is specifically connected now to VCF. And now we can start asking questions. So let's go back to the methods. For example, we could ask for, is there any information in this remote file for chromosome 7 in this position? So let's find out. So let's query. Let's do await, so we get the final response. And now we have V query, and inside the query we put the chromosome in the position. Here we go. Done. So again, a bit of a surprise, at least for us, that is so fast. I guess we have the HTTP and the web server developers to thank for this. And we find out there are at this location, 71510402080, we find out that there are in fact two records, one for the SNP and the other one for the SNP. And this is discussed here as well, so these are the same information. If you want to see the individual call, so just individual call, getting a range regardless of what may be in it, there is another method that comes handy. So we go here. Now we're not going to call it query. We're going to do a fetch. So let's call it range. Range, and let's fetch the compressed one. And now we just put a number. This number is going to be a position in the compressed volume. So let's put some silly number from 1 to 9. And now again, it feels almost instantaneous. It's in the sub-10th of a second range. So 1/10 of a second. And you see that interesting information is going to be the text. So this is a slice of the text inside the VCF file. Let's have a quick look at it. And there it is. So it goes for around 20K. That's the range gap that we found to be optimal. So this is discussed in the paper, of course. And you have that here. You see that the range sizes don't have an impact in the time it takes to retrieve them, up to a point, which is to be expected. Because at the extreme right-hand side of this graph, we would have the download of the whole file. So here we're just doing 20K of 16 gigabytes. And we find out that it's around 20K, we have a good number that is still not impacted by the transfer time, but it's not so small that you'd have to make many calls for the same query. So on that note, the last thing to have a closer look at is the algorithm itself. So we are pointing at positions in this volume, and this is in number of characters. And here we have the chromosomes. The example we have here is one where, so we have pointers at the boundaries. If we look for something here, the partition algorithm jumps to the middle, finds out that it overshot, and then walks back and forth until it converges to this value. But the next query, say for a position here, would benefit from a midpoint between here and here. So it's no longer searching in this space. So the more partitions we make, the faster the query becomes. And this is discussed and presented here. So we see an average time it takes to retrieve a query at the chromosome position. It starts by being around 120 milliseconds and then goes down to around 70, and presumably would keep going down until it approaches the value for queries that are already pre-cached, so queries where this range is already present. Now this is maybe best understood or appreciated. Let's close the developer tools and go to the notebook. Maybe better appreciated here. Alright, so some information here about how to load the library. So I'm not going to overlook all these details. The documentation is in GitHub. Just the important point is that all three main code loading methodologies for the web stack, so for JavaScript, are supported. Script tag loading, the traditional one, using CommonJS, or the modern ES6 import mechanism. So with this in mind, we have a plot here, beginning and end, and we have a query at position 5. And we find out that there are actually 2 hits here for this one. There it is, position 5, 2 hits for position 5 to 520. So let's find out where. So it should be somewhere here. This is projected. There it is. Let's try this with something much larger. And this is most likely a position that doesn't exist, so we're going to see hits 0. So here we go. Indeed, 0. Which doesn't mean that we don't have information. So if you look at the range, you'll find out that there is plenty of information about positions in the 15th chromosome that are retrieved from the large 16 gigabyte VCF file. Let's try a different value, For example, we could maybe do 11. Yeah, let's do 11. Actually, let's keep at 20, at 15. So enter, so we have nothing there. When we refresh the plot, there we are. If we now try 11, somewhere in between, so we expect some information here. Oop, forgot to press enter. And now refresh, and you see the new values here. So there is a line here that is being cached, such that subsequent queries, so one query generated an iterated method to find the right position, and in the process of going through these iterations, it populated a space that may be caching the responses to other queries. And let's see if there is anything else. I definitely encourage you to use the notebook and to use the landing page to try these different commands. The important point, and last time I repeat this one, is that we are looking at much faster times to retrieve content from a VCF file for which we have no index. So the scenario we are exploring here, which is the most common where we work, is that we have large collections of VCF files and no TabX companion indexes we can use. So this indexation has to be inferred iteratively by finding the beginning of the chunks, decompressing them, and then play the divide and conquer game until you find the answer. And I think I'll stop here. Please feel welcome to reach us in Gitter, and we're happy to help you with any use of these libraries. All right, bye now.